Hello, International Conference on Information Intelligence Systems and Applications. I wish I could be in Greece right now, but alas, I'm just a video recording. Hello, my name is David Ramirez. I'm excited to speak to you about my paper and research, Infrared Computer Vision for Utility Scale Photovoltaic Array Inspection. It's a mouthful. I'm working in collaboration with Pujara, Professor Cihan, Dr. Srinivasan, and Professor Andreas Spanias. Solar power has become an important aspect of utility companies' energy portfolio. But utility scale photovoltaic arrays come with some unique challenges. Uh, when you have thousands of solar panels all together in an area, this becomes a logistical problem with regards to monitoring any sort of damage that may occur there. Uh, Photovoltaic cells and sort of photovoltaic panels might be damaged through a number of reasons: manufacturing defects, um, damage in shipping or installation, as well as extreme weather events, environmental conditions, or just age in operation of a solar panel. Faults may occur, um, present themselves as semiconductor wear, glass cracks, micro cracks in the silicon, delamination of epoxy holding the solar panel together, which can introduce water into the electronics, as well as diode failure, which is a common fault here in solar panels. Many of these faults produce heat instead of electrical energy. Faulty photovoltaic cells and panels not only cause a degradation in that localized area, but they can cause several other cells in that series or in parallel to become reduced as well. In some of the figures at the right, you can see one prominent cell going bad, taking the entire series of cells into a degraded state. It has a disproportionate amount of efficiency loss when any sort of error occurs. This is true of larger scale as well, where several panels might be affected due to the performance of just one of the panels. We want to detect these hotspots with thermal cameras, also known as thermography, and that's going to be the primary method for us to do evaluation of these in the field. For motivation, thermal cameras have become increasingly popular due to the reduced price, which has come about through manufacturing advances. Flying drones might have thermal cameras attached to them and be operated by inspection technicians. We would collect thermal imagery across a wide area, and then there would be some manual analysis to identify faulty solar panels within that large scale of the utility plant. Precise scanning, though, to identify the very particular individual panels still can be labor intensive and might require hands-on to electrical testing to see the state of the panels. We would like to have automated monitoring methods to improve power generation and reduce downtime, which you might achieve through sensors or perhaps through computer vision methods. There is a need for these automation to reduce the costs associated with maintenance and operation of solar panel plants, as well as just increasing the overall cost efficiency of such a utility scale operation. Not only do we want to detect large dangerous faults, but we want to also detect and diagnose degradation, more subtle efficiency loss in solar panels. Thermal imaging has been studied in literature, including computer vision, machine learning, deep learning methods, which we detail in our survey of this material in our paper. Solar module grading, though, is a fairly new concept, which we believe is still a lingering challenge for this area, something that we're pursuing. The ability to grade the effectiveness, the efficiency of a solar panel based only on its thermal imagery characteristics. So our proposed method, we want to use thermal imagery which doesn't have a laboratory collection methodology. We want to use photographs that are taken from a variety of different angles, such that an algorithm like this could be robust for a lot of different view angles, and perhaps see more use in a field in the wild applications. Some of our processing methods here. We want to detect the different hotspots associated with photovoltaic array. So the notional array on the left shows several different faults, including a checkerboard, um, faults in series, as well as large swaths of potentially damaged faulty um, photovoltaic cells. The data processing steps that we use to detect those are um, using a handheld, for now, camera to take a thermal image. We want to do panel detection to segment out one panel at a time for analysis, which can be seen in the process on the right of the image. We will transform this through a perspective transformation, rectify it to be the original aspect ratio of the solar panel. Then we will stretch the contrast to exaggerate hot spots using a histogram equalization method. Finally, we can apply different anomaly detection techniques, such as object detection or a more simple thresholding method. So this is the thermal camera that we're using in this data collection and experiment. It's a consumer grade, modestly priced thermal camera that you could pick up at your local hardware store. This allows us to collect fairly high resolution thermal imagery, which we will put through our computer vision algorithm. The first step being a canny edge detector, as seen in the red outline on the right. This highlights the edges of high contrast, where then a Hough transform is used to place straight lines through the image, which attempt to match those edges as best as possible. This builds out our framework for segmenting individual solar panels. We compare the predicted Hough transform blue lines with the ground truth green lines that have been manually annotated to the dataset. We use this to evaluate the overall performance of the algorithm. We've created an evaluation dataset of 117 thermal images, 755 photovoltaic array grid lines, dividing panels, as well as over 1,000 intersecting key points of corners and 900 photovoltaic panel polygons. We have divided the results into 4 categories, both a true positives detection class category, as well as near misses, where a predicted line was drawn but exceeded a threshold associated with the angular distance of the proposed line compared to the ground truth line. We also are tracking type 1 error, false positives, as well as false negatives, the type 2 error, aka missed detections. If you took all this information, we could simplify it further into a confusion matrix, or by adjusting the threshold parameter on our angular distance threshold, we could create a precision recall or ROC curve to have more fine detail associated with our detection characteristics. In future work, we would like to compare this Hough method with other methods, perhaps of different categories. If we can compare the data points associated with here to bounding boxes and key points, and as well as other line generating methods. All these data points can be translated into other formats and used for comparison. We would then take these segmented imagery, do a perspective transformation to return that to the original aspect ratio. In this image at right, you can see that a bounding box has been drawn around areas which show higher than average heat characteristic. But hidden behind my speaking face here, there is a bypass diode, another hot electronics, which we would not like to detect. And so it's necessary to detect only some hot things and disregard others associated with these photovoltaic panels. Additionally, we can segment on a pixel by pixel level the potential hotspots in more fine detail. I say potential because there is the potential for errors. The glass surfaces associated with solar panels, they reflect infrared radiation from the sun, from other objects illuminated by the sun, which becomes a challenge. We want to track the collection angle associated with our camera compared to the angle and geometry of the solar panel in view, also compared with the sun and any other opportunities for it to reflect off of other surfaces. The uh, manufacturer of thermal cameras recommends that only some angles are appropriate for capturing infrared photography, and something to be mindful of. The the image data, it can be combined with electrical sensors, power meters, as well as the photovoltaic panel's age and overall wear, um, eh, being able to associate um, degraded performance. What we would like to do is take this imagery, thermal imagery, and combine it, pair it with these performance characteristics to create a supervised machine learning data set for a regression problem. This would allow us to grade the performance of a solar panel based only on its thermal image characteristics. We could estimate the potential performance on a panel by panel basis and recommend panels for replacement, which might be past their prime. Here are some of the references I used in this presentation. Many other references in the research paper. Here I'm often pulling source material from the FLIR thermal camera manufacturer. I would like to acknowledge the National Science Foundation, the Sensors, Signals, and Information Processing Center, and Poundra LLC. If you have any questions, please contact me at my university email address. Thank you very much for your attendance.